The next two transfer functions that we still need to consider, well, the first one is a transfer function that has a complex pole of a pair of complex poles, and the other one is a transfer function with a complex pair of zeros. And after considering these two transfer functions, you should be able, or should have, the tools or building blocks to be able to draw the Bode plots for any transfer function. But in this video I'll consider the transfer function that has a pair of complex poles, and in the next one I'll consider a transfer function that has a pair of complex zeros. Okay, a transfer function that has a pair of complex poles will look something like this. The T7 of S is equal to omega b squared over S squared plus 2 zeta omega b s plus omega b squared. Alright, but we want to rewrite this into a form that makes it easy for us to do the Bode plots, and we can rewrite this into the form 1 over S over omega b all squared plus 2 zeta S over omega b plus 1. Okay, again, this omega b is the break frequency. Okay, of course the first step is we need to set S equal to j omega. So if we do that, we get just put the subscript there. So we get 1 over j omega b, j omega over omega b all squared plus 2 zeta j omega over omega b plus 1. And if we take the square of the first term, we can rewrite it like this. Negative omega over omega b squared plus, take out the j, 2 zeta omega over omega b plus 1. Okay, we want to rewrite this into the standard complex form of a plus jb, and we can easily do that if we multiply the top and bottom by the complex conjugate. So let's just rewrite this out. Omega b all squared plus j 2 zeta omega over omega b plus 1 times, well, there's two real parts in there, we can group them together. So squared minus the complex part b. Well, I think I'm going to make it easier on myself. Just copy this part. Okay. And if we do the maths, you should get something like this. Oh, I may need more space. It's equal to 1 minus omega over omega b all squared over 1 minus omega over omega b squared, and that all squared, plus 2 zeta over omega b, and that all squared. I'm going to copy this again. And that numerator should be 2 zeta omega over omega b. Okay, and there's still a j term. Let's put the j term there. Okay, so that's our frequency response transfer function. After we set s equal to j omega and then put it into the standard form a plus jb. And this is the real part, and that's the imaginary part. Okay, at this point in time I'm going to start on a new page. I'm going to use a new page to draw my Bode plots, just because we're going to have to come back to them every time. So let's try and do this neat. Okay. The decibel scale and then the angle. Okay. So I'm going to quickly go and borrow this frequency response transfer function that we worked out. Okay, at this point in time it's actually easier for us to first consider our three cases. We're going to consider three cases. We know that our omega b is somewhere here. So we can consider three cases where omega is much smaller than omega b, where omega is equal to omega b, and then the case where omega is much greater than omega b. Okay. But it's easier for us to first consider those cases before we try and simplify our transfer function or find the magnitude and phase of this transfer function. So let's consider our first case. Let's draw a line. So case 1, where omega is much smaller than omega b. Okay. If this is the case, then the ratio omega over omega b is very small, to the point where we can say that, alright, it's approximately equal to 0. And if we look at our frequency response transfer function, we can simplify it as well, this term goes to 0, so we've got at the numerator of our real part 1 minus 0. In the denominator, for the first term, again we've got 1 minus 0, and then for the second term in the numerator, that's of course equal to 0. For the imaginary part, well, this in the numerator, the term omega over omega b goes to 0, so the numerator is just 0, so whatever is in the denominator, well, I guess we have to consider if it's 0, but we can see it's not equal to 0, because we've got a 1 there minus 0 plus 0. Okay, so the frequency response transfer function then just simplifies to 1. Okay. So if we take the magnitude of that, well, that's 20, no, that's of course the real part squared plus the imaginary part squared. We've got a 0j there. Then obviously the magnitude is just equal to 1. The phase, well, so over here, so for of course equal to the arctangent of the imaginary part over the real part. Let's have a minute look. Alright, so we've got a negative imaginary part there, but it's 0, so that is, the phase angle is just 0 there. Okay, so for frequencies much smaller than omega b, we see that the magnitude is equal to 1. If you want to go draw the Bode plot, we have to take 20 log of that, and that is just equal to 0. So for omega smaller than omega b, we see that the magnitude is 0 dB, and the phase angle is also 0. So we can go draw that on our Bode plot. Let's use color. Okay. So for very small angles, we see that our magnitude is 0 and our phase angle is 0 as well. Okay. We have to consider the next case, a case when omega, let's first consider when omega is much greater than omega b. Well, in this case, omega over omega b, if omega is much larger than omega b, then this is a very large term. So we can say, well, if we look at 1 minus omega over omega b squared, then we can deduce that, well, this is a very insignificant term, the 1, and therefore that approximates equal to minus omega over omega b squared. Okay, let's have a look here. Why did the 1 minus omega? Because we've got a lot of 1 minus omega over omega b squared terms in our frequency response transfer function. Okay, so if we use this approximation, then we can rewrite our frequency response transfer function as the numerator in the real part just gets approximated by negative omega over omega b squared, and the denominator, the first term in the denominator as well. So we've got a negative omega over omega b squared plus then that 2 zeta omega over omega b, and that all squared. And the real part, the numerator just stays omega over omega b, and the denominator is of course the same as the real part. Okay. When we look at this frequency response transfer function, we can see that these terms in the denominator is much smaller than this first terms in the denominator. Since it's this term is squared, the second term in the denominator, so that term is squared, while this term is raised, the first term is raised to the power of 4. Okay, so we can neglect that term safely. So we can get rid of that. And then we can approximate our frequency response transfer function as negative omega over omega b squared over the first term in our numerator, while that squared term gets rid of that negative term, so we left with omega over omega b to the raised to the power of 4 plus 2 zeta omega over omega b over again eliminate that negative squared. We've got a negative there. Okay, and then we can obviously cancel some terms there, and I'm going to rewrite it in this form: omega over omega b to the power of minus 2 plus negative 2 zeta omega over, I think I made a mistake somewhere. Oh yeah, that's correct. This should be a 4. Okay, so then this just becomes negative 3. Okay, we can from this we can find the magnitude and phase. So this is Tj omega. So let's find the magnitude first. Of course, that is the square root of, sorry, I think I've missed a j over there. So that's the real part squared plus the imaginary part squared. So we've got negative omega over omega b, that's squared, plus minus 2 zeta omega over omega b to the power of minus 3, and that's all squared. Okay, just going to get rid of this irritating text. It turns out we can actually simplify this magnitude function, noting that this second term is much smaller than this first term. Since it's raised, this term is raised to the power of -6, and this term is raised to the power of -4. So we can simplify this by neglecting that term, and then we can just rewrite this magnitude as omega over omega b. Okay, and that, of course, this square term gets rid of this negative, so our magnitude then just becomes equal to omega over omega b power of -2. Okay, let's just quickly rewrite this out. Okay, to plot this, on a Bode plot, we obviously have to take 20 log of that. So let's take that, 20 log of magnitude, and well, that's 20 log of omega over omega b, and that is, of course, we can bring down the -2 in front of the log. That becomes -40 log of omega over omega b. Okay, so at this point in time, it's probably easy to just quickly draw a small little Bode plot here, so we can see what this behavior of this magnitude function is. So we're looking at frequencies far greater than omega b, so we're looking at this region. Okay, so let's plot a few points to see how this magnitude plot behaves. So let's do it here. So omega and then 20 log of the magnitude of the frequency response transformation. Okay. So if we take first for, let's say when omega is equal to omega b, well then this omega over omega b just becomes 1, then that's -40 log of 1, and that is of course 0. When omega is equal to 10 times omega b, well then it just becomes -40 log of 10, and that is just equal to -40 dB. And then when omega is equal to 100 omega b, it just becomes -40 log of 100, and that is equal to -80 dB. Okay, and if we plot those points in our little graph, when omega is equal to omega b, then our magnitude is 0 dB. Okay, when omega is just plot those, whoops. 10 omega b and then 100 omega b. Okay, so when omega is 10 omega b, then our magnitude is -40 dB, and when it's 100 omega b, it's that's -40. And when it's 100 omega b, it's -80 dB. Okay, so we see that we've got a straight line that has a gradient of -40 dB per decade for omega much more larger than omega b. Okay. We still have to calculate the phase. well, we have to quickly go look back at our frequency response transfer function. For case 2. Okay, so this is our frequency response transfer function. Let's quickly copy that for sanity. Alright, so our phase is just the arctangent of the imaginary part, which is -2 zeta times omega over omega b to the power of -3 over negative omega over omega b to the power of -2. And we can simplify this a little bit in, if we do that, well, we get those negatives cancel, so we've left with 2 zeta, and we're left with 1 of the omega over omega b's. Okay. Now, as omega gets much larger than omega b, then of course this will tend towards infinity. That means this will sorry, I had to, this is to the power of -1. Alright, so apologies for that. Okay, so as omega gets larger and larger, or larger than omega b, this term becomes so large, and that means we're left with a tan of -omega1 of 0. And that means that's equal to 0 degrees, but that's actually not correct, because we have to take into account the quadrant in which our complex number lies, or our frequency response transfer function. And we see we've got 2 negatives there, so it's lying in this quadrant. Okay, so in fact our phase angle is not 0, our phase angle is -180 degrees. Okay, so we see when omega is much larger than omega b, we've got a constant phase angle of -180 degrees, and our magnitude, where did I plot that? Our magnitude falls from the omega b frequency and falls by -40 decibels per decade. Okay. So our magnitude falls by 40 decibels per decade from omega b. Let's draw something like this. and our phase, let's call this negative 180 degrees. And we know that it's a constant negative 180 degrees from omega b. Okay. We still have one case left that we have to consider. That is when omega is equal to omega b. Okay, we still have to go back to our original frequency response transfer function, which is this one. I'm going to quickly copy that. Right. Okay, so when omega is equal to omega b, well, the ratio omega over omega b is then just 1. Then our frequency response transfer function can simplify quite a lot. Then in our numerator of our real part, we've got 1 minus 1 is equal, well, that's then just 0. So in the denominator, we've got 1 minus 1 again, and we've got a plus to zeta in the second term of our real part in the denominator, plus j times minus 2 zeta in the numerator, and then we've got the first term of the imaginary part in our denominator. We've got 1 minus 1 plus well, we've got 2 zeta squared. Okay, so this is equal to 0. So we've got 0, and we're left with the imaginary part. Then one of the zetas cancel at the top, and the 2 at the top cancel, and we've got a negative 1 over 2 zeta. Okay, oh, got still a j term there. So this is our frequency response transfer function when omega is equal to omega b. Okay, so we first have to then to take the magnitude of that function. Well, if we do that, real part squared plus imaginary part squared, that just turns out to be again 1 over 2 zeta, and I'm going to rewrite it in the form 2 zeta to the power of negative 1. If we want to plot that on the Bode plot, we have to take 20 log of that. So if we do that, we can bring down the negative 1 in front of the log, so that just becomes 20 log of 2 zeta. Okay, so that's a magnitude function for plotting on the Bode plot. Okay. Now for this specific case, when omega is equal to omega b, the magnitude plot will look well, the look of this plot, or the behavior of this plot, will depend on zeta. And what this means is, if you remember, zeta is your damping coefficient or damping ratio, and that means this magnitude function will the behavior of this magnitude function will depend on how much damping you've got in your system. If I can, for example, let's plot a few, or analyze a few values. So let's take zeta, 20 log of this 2 zeta And let's just write down some effect. Okay, so we've got a 2 in here. So if we say, alright, if zeta is equal to 0.5 or a half, then then this minus 20 log becomes just 2 zeta becomes minus 20 log of 1, and that's of course 0. And that means your magnitude is of course then this 0, the magnitude is 0, and that means the magnitude behaves or traces out on the 0 dB line. So on 0 dB line. Okay, when zeta is greater than 0.5, well, what the effect of that will be as we have a negative, we have more of a negative gain at the break frequency. So okay, I'll when we plot this, I'll show this effect on the plot. Okay, so when zeta is smaller than 0.5, in that case we have a peak. The effect of that will be there will be a peak of negative 20 log of 2 zeta at omega b, and I will show this on the graph. And well, when we've got no damping in our system, then well, we take 20 log of 2 times 0, well, that's just infinite, so we've got an infinite peak at omega b. Okay. Before I'm going to plot this this magnitude function, I quickly just want to work out the phase. If you recall, of frequency response transfer function looks like that. It's negative 1 over 2 zeta j. So our phase will be just the arctangent of minus 1 over 2 zeta, which is the imaginary part over the real part, and that was 0, and that is just equal to tan of negative infinity, and that's negative 90 degrees. Okay, so at omega b, our frequency, our phase angle is negative 90 degrees. Okay. So let's keep this in mind. This is the magnitude and that's the phase. Okay. Let's go and plot this on our graphs. Okay. So our magnitude function was minus 20 log of 2 zeta, and our phase was at omega b was negative 90 degrees. Okay, so as I've said, the form of the magnitude, or the behavior of the magnitude, depends on your zeta. Now, if we've got the zeta of 0.5, then, well, then our omega b is just on the 0 dB line, as I said before. If we've got zeta greater than 0.5, then we've got a negative gain at an omega b, and that means that will look something like that. So our gain will be negative there. But if we've got a zeta smaller than 0.5, we will have a peak at omega b. There will be some peak at our omega b. Okay, so if we draw the real function or Bode plot magnitude function, it will look, oh, let's use another color. It will look something like this. Okay. But usually we don't draw that, we just approximate it as these straight lines. Okay. Drawing the phase plot is a little bit more tricky. We see that for small frequencies we've got a phase angle of 0 degrees, and for large frequencies we've got a phase angle of negative 180 degrees, but here at omega b we've got a phase angle of negative 90 degrees. So somewhere between these two, the phase line should break away from these 0 degree line and negative 180 degree line. And where that happens is, just like in the previous case, we do approximations, and we approximate it as omega b over 5 to the power of zeta, and where it connects to the negative 180 degree line, well, we approximate that as omega b times 5 to the power of zeta. We can do this because we know at low frequencies the phase is 0, at high frequencies the phase is negative 180 degrees. And if you plug these values in for low frequencies and high frequencies in our phase function, we can see that it will give approximately 0 degrees and approximately minus 180 degrees. Okay, so we can then, I'm going to use a different color to make this clear. Well, let me first draw how the real phase plot will look like. It will look something like this. Oh, I'm going to have to redraw that. Okay. But our straight line approximation will look something like this. Okay. So we've went through a lot of maths. But when you've got a transfer function in your, or a transfer function that has a pair of complex poles, then you know that depending on your zeta, you will have to look at how this part at omega b looks, but you know that up to the break frequency approximately you've got 0 gain or 0 dB, and then after omega b you've got a negative 40 dB per decade drop off. The phase of that, well, you know you can approximate it by these three lines, and you know that you will have a 0 degree phase up to omega b over 5 to the power of zeta, and you will have a negative 180 degree phase up to omega b times 5 to the power of zeta. And you also know you will have a negative 90 degree phase at omega b. Okay.